Alright, after a short interlude, here we go, matrix algebra. So now we've talked about matrices. We have a bunch of properties of matrices, and so now we turn the tables and start looking at what we can say about matrices as if they're numbers or something, or just sort of at a symbolic level. And the first thing is, and I've mentioned this already in class, but the 2 by 2 matrix 1 0 0 1 behaves as behaves like the number 1. It's the multiplicative identity for the matrix multiplication. So this times that, that times that. So in other words, IA is equal to A, and AI is equal to A again. All right. I'm trying to set my timer here. All right, so we've mentioned this before. One thing I should mention, if we have a matrix such that AB is equal to BA is equal to I, and we have another matrix such that A times C was equal to C times A was equal to I, then that forces B and C to be equal. All right, so suppose you have both things are true, then if I multiply both sides by A, I get AB equals to AC. If I multiply this on the left by B, I get BAB is equal to BAC, but remember, BA is equal to I, right? So that gives me IB. On the other hand, AC is equal to I, so that gives me IB is equal to IC, but remember, I times B is B again, and I times C is C again, so that gives us that B is equal to C, so there you go. All right. Anyway, long story short, if AB is equal to I, we do not write B is equal to I over A. I mean, you can write it if you don't like your points, but if you like to keep your points, you won't write that. We have a definition that we use here, which is that if AB is equal to I and BA is equal to I, if there exists a matrix B for a given square matrix A, that these two conditions are met by B, then we say A is invertible, and we say that A inverse is equal to B. All right. Invertible matrices are also called non-singular. If a matrix has no inverse, then it's a non-invertible or a singular matrix. So one of the things you ought to know, you might know from a previous course already, is that if we have a sorry, I need to get a cover sheet here to focus our attention. I forgot to grab it before I started. My apologies. So one of the things that's often useful to know is how to invert a 2 by 2 matrix, all right? So if you think about it, we're just trying to, if we give an ABCD, we're trying to find a B equal to XY, ZW, such that AB is equal to I and BA is equal to I. If you study that equation, the algebra leads you to X is equal to D over T, Y is equal to minus B over T, Z is equal to minus C over T, W is equal to A over T, where T is equal to AD minus BC. Now that, in particular, we could write like so. The inverse of the matrix ABCD is 1 over AD minus BC. And so what we do is we flip the diagonals, we put minuses on the off diagonal. That gives us an inverse. Now, if you don't believe me about the algebra, we can check and see that the formula really works. So multiply the alleged inverse matrix by the matrix. All right, and all I did is I pulled the 1 over the AD minus BC term, which, by the way, this is the determinant of the matrix. Pull that out to the left of the multiplication. Multiply these two matrices, we get that. The off diagonals cancel to give me 0, and on the diagonal we get the determinant and the determinant again, but then by scalar multiplication, assuming that this is non-zero, we get 1 0 0 1. And you can do the opposite multiplication to show BA is equal to I. It's very similar. Now, I should mention AD minus BC is called the determinant of A. If we're working over the real numbers, the significance of the determinant is it tells us the area of a parallelogram that would look like, if you had a parallelogram like this, say this is the AB vector, and this is the CD vector, right? And you make a parallelogram like this. All right. So in this case, if we rotate AB in the direction of CD, that's a counterclockwise rotation, right? And so the determinant of A, B, C, D, well actually it's also equal to the determinant of A, B, C, D. It doesn't matter. If you look at the vectors either as rows or columns, it doesn't matter because the determinant of a transpose is the same as the determinant of a matrix as it happens. In either case, this is the area of the parallelogram. All right. If on the other hand, the picture was like this, right? So in other words, this was a clockwise rotation, then the determinant of AB, oops, sorry, I'm writing off the page, my bad, ABCD would actually be equal to minus the area of P. So the sign of the determinant tells you whether or not the columns are related by clockwise or counterclockwise rotation if we're talking about a real matrix. Now, this formula works just as well for matrices over something else. So let me just throw in an example here, not in the notes, add some value here. So example, if we're working over, say, Z4, all right, and we had the matrix A is equal to, I don't know, 1, 2, 0, 3. All right, in this case, the determinant of A, and I guess I should put bars on it just to emphasize what I'm doing. The determinant of A is 1 bar, 3 bar, 1 bar times 3 bar minus 0 bar times 2 bar, which is equal to 3 bar. Now, fortunately, 3 bar has an inverse. So what's 3 bar inverse equal to? Well, it's equal to 3 bar again, since 3 bar times 3 bar is equal to 9 bar, which is equal to 1 bar we're talking about Z4 calculation, right? Great. So if I look at the matrix 1 bar, 2 bar, 0 bar, 3 bar, the inverse of it, the formula, so this formula has to be interpreted as AD minus BC inverse in the case that we don't have a agreement about 1 over something meaning something. So this is the notation which is used for Zn for the reciprocal, okay? So this formula looks like that in Zn, assuming of course that the determinant exists. In this case, in my example, it does. And so anyway, getting back to the point here, so we have 3 bar inverse. I'm supposed to flip the diagonals, put minuses on the off diagonal. All right, so that's actually 3 bar, 1 bar. What's minus 2? Minus 2 is 2 in Z4 because we add 4, we get 2. This is 0 bar, of course, and then of course this gives me 9 bar, 6 bar, 0 bar, 3 bar scalar multiplying, which we can simplify to 1 bar, 2 bar, 0 bar, 3 bar. This is the alleged inverse of A. Let's see if it works. A times A inverse equal to 0, oops, sorry, I can't remember my matrix. 1 bar, 2 bar, 0 bar, 3 bar, 1 bar, 2 bar, 0 bar. Whoa! Check it out. Apparently, A is its own inverse. Cool. Anyway, let's see if it works. So this times that gives me 1 bar. This times that gives me 0 bar. This times that gives me a 1 bar times 2 bar plus 2 bar times 3 bar. So that's 2 bar plus 6 bar, I suppose. And then down here we've got 0 bar plus 3 bar times 3 bar, which is 9 bar. Let's clean that up a bit. This is 8 bar, which is 0 in Z4. So we have 1 bar, 0 bar, 0 bar, 1 bar again, because this is 9, which is 1. And of course that is the identity matrix in Z. Well, this is the identity in what I would call Z4 2 by 2. It's the identity matrix in Z4 2 by 2. All right. So yeah, I mean this neat little formula for 2 by 2 matrix inverse even works over Zn. So it's a surprisingly flexible formula. So I thought I should throw that in there for you. I have a couple of less esoteric examples down here. So next up, I mentioned that another nice example of the inverse formula has to do with the, I'm trying to get back my cover sheet. Now it's got some writing on it, but it'll do. If we look at the matrix cosine theta minus sine theta cosine theta, and we study what that means, this corresponds to a rotation in the plane by angle theta counterclockwise. And if you calculate the inverse of that using the standard formula, we end up with sine squared plus cosine squared in the denominator, also known as 1. And you know, switch the diagonals, minuses on the off diagonal. But then if I use the even and odd property of sine and cosine, I can look at this as being cosine of minus theta, sine of minus theta, minus of minus sine of minus theta, cosine of minus theta. In other words, this is a rotation by minus theta, which makes perfect sense, right? If you want to undo a rotation by theta, you rotate by minus theta. So it's kind of a very satisfying result, right? Now, non-invertible matrices challenge our intuition. If A inverse does not exist for A, it's possible to have AV equal to AW, yet V not equal to W. Here's an example. 1, 1, 0, 0. If we look at AE1, it's equal to 1, 0. If we look at AE2, it's equal to 1, 0, right? So AE1 is equal to E1, and AE2 is equal to E1, but obviously E1 is not equal to E2, right? So if it's a non-invertible matrix, we can't cancel. We don't have a cancellation property, all right? Now, here are some properties for inverse. AB inverse is actually B inverse A inverse. This is very much the same reasons as like the composition of functions has a similar rule, right? If you look at F composed with G inverse, it's G inverse composed with F inverse for much the same reasons. But here's the proof, if you like. A, B times B inverse A inverse equals to A, B, B inverse, A inverse, using associativity of matrix multiplication. That's AI, A inverse, which is A inverse, which by definition of inverse is I again. And very similarly, you could show that B inverse A inverse times AB is equal to I, likewise. All right. In the next chapter, we'll prove that if you have left cancellation, you automatically have right cancellation. So, but anyway, one thing at a time here. For the moment, our definition of inverse requires us to show both of these conditions hold, all right? So other properties of inverse, if we have a non-zero scalar times a matrix, then the inverse is the reciprocal of the scalar times A inverse. Of course, if we're in Z mod n, then this should be understood as C inverse. If it's an invertible matrix, we do get cancellation on either side. And also, transpose and inverse work together nicely. The inverse of the transpose is the transpose of the inverse. That can be shown. And inverse is also like transpose in that the inverse of the inverse is the matrix again. All right. So the proof is given here. Let's look at the proof of 5. Or maybe well. Let's look at this. Finally, if A inverse is equal to I, then if we hit this with the transpose, take the transpose of A inverse equal to I, that gives us that A inverse transpose times A transpose equals to I transpose. But the transpose identity is identity, right? So what's this show? This shows that the inverse of A transpose is equal to A inverse transpose, right? Which is what we're trying to show for 5. Another thing I should mention, moving on here, you know, one thing you might notice is all of a sudden we're not using we're not looking. I mean, I've been talking about ijth component all day long, right? All of a sudden I'm not talking about the ijth component, right? So part of this course is learning what kind of argument you want to use, right? Like this is not something you want to look at the component level of, right? We're using matrix level arguments, and that works here. This one, if we have a product of invertible matrices, it's invertible, and this is the socks shoes rule, which you can prove by induction, as I do here, right? So suppose it's true for some k greater than 2. Look at the product of k plus 1 things. I think of this first bunch as being B. Then I've got BA to the k plus 1 inverse, which by what we've already proved is, you know, AK plus 1 inverse times B inverse. But then by the induction step, I can rewrite B inverse like that. Plugging that back into there is exactly the claim for k plus 1. So induction is often a useful tool for proving something like this. Moving on, matrix powers. So the 0th power of a matrix, so we're talking about square matrix here, all right, over a commutative ring with identity. The 0th power of a matrix is defined by identity. The first power is defined to be the matrix. And then for positive m, we recursively define a to the power m to be a times a to the m minus 1. Furthermore, if a is invertible, then we define negative powers by the power of the inverse. All right, like that. For example, a cubed would be a times a squared, which would be a times a, or That's how I feel right now, right? Don't feel that way. This will soon be done. So a to the p times a to the q is a to the p plus q. All right. A to the p to the q is a to the pq. Great. And if a is invertible, then we have the laws of exponents for integer exponents. The proof of these things is not especially exciting. I'll let you read it. It's just a matter of induction, pretty much, and the definitions, which I just stated. Mostly you need to be aware of these and, you know, how to use them. So it is important to know the definition of matrix power because that comes up later, but you know, I'm going to move along here. One thing I should mention is that when a and b don't commute, then like ab squared would be ab times ab, and if b times a is not equal to a times b, I can't rewrite this to get a squared b squared, right? And likewise, ab cubed is actually ab, and so forth. So if you look at that, a plus b squared, likewise, was this times that, which if we look at that is actually a squared plus ab plus ba plus b squared, right? In other words, the binomial theorem fails, right? It's not the case that a plus b squared is a squared plus 2ab plus b squared. Now, if a and b do commute, then you can prove the binomial theorem holds for matrices as well. But they don't, generally speaking, two square matrices aren't going to commute, so we have to be careful not to misapply the binomial theorem. Just a word of caution there. So we're getting near the end here. We have just a little bit more to cover. So these are special. So the remainder of this chapter is basically about matrices with a particularly special shape they're a nice example for different things we study in this course, and we keep coming back to this. This is something you need to know from here on out, like what's a symmetric matrix, what's an anti-symmetric matrix. So here's the definition. A matrix is symmetric. A square matrix is symmetric if it's equal to its transpose. It's anti-symmetric if it's equal to minus its transpose. All right. So at the level of components, it means that aij is equal to aji, whereas this anti-symmetric means that aij is equal to minus aji. One thing you can see immediately from that is if you have a transpose equals to minus a, then if you look at the ith component of that, that means that aii is equal to minus aii. What does that say? That says that 2 aii equals to 0, and so as long as we're not in some kind of weird number system where 2 is 0, right? If 2 is not 0, then this means that aii is equal to 0. In other words, anti-symmetric matrices have zeros on their diagonal. All right. So that's, you know, a useful fact. Here's some specific examples. The identity, the zero matrix, EII. So that puts a 1 on the diagonal, zeros elsewhere. 1, 2, 2, 0. These are all symmetric matrices. 0 is also antisymmetric, as it happens. 0 is both symmetric and antisymmetric. In fact, 0 is the only such matrix. You can prove that. Then these are neither symmetric nor antisymmetric. I mean, that's not even square, so you can't hope that it's symmetric or antisymmetric. But you can take any matrix, no matter square or not, and if you take any matrix, m by n matrix, and multiply it by its transpose, like so, A transpose A, well, that is itself a symmetric matrix. So it's always easy to take a matrix and create a corresponding symmetric matrix by this. Here's the proof. You take the transpose of A transpose A. Sock shoes, A transpose A transpose transpose, which is A transpose A, because the transpose of the transpose is the matrix again. And there you go. The transpose of this matrix is equal to that matrix again, which shows you that this is a symmetric matrix. This next proposition is a nice example of a induction. So here's the claim. A is symmetric implies that A to the power k is symmetric for all n. First of all, the base case of k equals 1 holds true because the definition is that A to the 1 is equal to A, right? So suppose it's true for k. Suppose A to the k is symmetric. Look at A to the k plus 1. So A to the k plus 1, by definition, this is what I was talking about a second ago. You need to know the definition of matrix power, right? So A to the k plus 1 is A times A to the k. And if we transpose that, then by sock shoes, this gives us A to the k transpose times A to the k. Then by the induction hypothesis, we know that A to the k transpose is A to the k because, remember, if A is symmetric, A to the k is symmetric is the induction hypothesis. So A k transpose being A to the k is the induction hypothesis. And now A is symmetric, so A transpose equal to A. But then again, by definition of matrix exponents, we get A to the k plus 1. Thus, by proof by mathematical induction, A to the k is symmetric for all k and n. This is a pretty nice test question. I've asked it before. So next up here, we have triangular and diagonal matrices. So here again, we just finally got away from the index notation. We're going to come back to it here. It helps us again. So diagonal matrix means that it's non-zero. It's only non-zero on the diagonal. It's 0 elsewhere. You can also talk about upper triangular or lower triangular, and it's just what it sounds like. So here's some examples: diagonal, upper triangular, lower triangular. All right. If the diagonal of a matrix is 0, then the matrix is hollow. So we just proved a second ago that a antisymmetric matrix is hollow. But honestly, this is pretty much, I don't think I ever talk about hollow anywhere else in these notes. So there you go. Fun fact, you can take any matrix, and you can of course write it as a sum of a strictly upper, strictly lower, and diagonal matrix. And the proof, again, is really almost immediate from the matrix units. You just decompose it. You know, you got the diagonal piece, and this would be strictly lower diagonal. This would be strictly upper diagonal. And there you go. That's a diagonal. Again, strictly lower, strictly upper, I think. And there you go. I mean, it's kind of like old... in fact, any matrix can be factored into a LU decomposition. Well, it's not any matrix. Actually, there's some fine print attached here. For the sake of irony, I don't cover that in this course. So here's what happens in the 2 by 2 case when we multiply. See it a bit? Triangular matrices. She's outside. You going out? So here we have a 2 by 2 matrix times a 2 by 2 matrix. This is lower triangular, multiply them together. Guess what we get? A lower triangular matrix. Over here, we have upper triangular times upper triangular. What do we get? A upper triangular matrix. So apparently the product of lower and lower is lower, the product of upper and upper is upper triangular. And as I've mentioned to you guys, what happens in the 2 by 2 tends to happen in the n by n, and we can prove that, in fact. Although I don't have a 2 by 2 example of the diagonal case, but in fact, if we have a product of the diagonal matrices, then the product is diagonal. A product of upper triangular matrices is upper triangular, and a product of lower triangular matrices is, in fact, lower triangular. All right. So here's the proof of the diagonal case. If it's diagonal, I can write A as AI, EII. So that would be like this. A is equal to A1, A2, da da da, AN. B in my current notation, B1, B2, da da da, BN. Since they're diagonal, I can write them like that. And zeros elsewhere. Multiply them. So I just took the numbers, pulled them out, and that gives me EII times EIJ. Remember I said it's useful to know about how to multiply these? Well, here's one of those places. So this is chronicle to IJ, EIJ, by the all your base are belong to us subsection. And of course this is only going to be non-zero if I is equal to j, so I just collapse the sum over j down, and I get AI, BI, EII, which shows you that what could be simpler? AB is actually equal to A1, B1, A2, B2, da da da, AN, BN. So not only is the product of diagonal matrices diagonal, it's sort of the stupidest possible thing, and the new matrix is just formed by multiplying each diagonal entry, respective. Now the proof of 2 actually is kind of a triumph of index notation, I would say, and here it is. So I have two upper triangular matrices, which means I can write them in terms of a sum over I less than or equal to j, or sum of k less than or equal to L. All right. If you look at the footnote, I explain what that means precisely for a low dimensional case. And so using properties of sums, I just break it out: sum over I less than j, sum over k less than L, pull the numbers together, Aij, Bkl, and that gives me a Eij, Kl again. But remember, this simplifies to Kronecker delta Jk, Eil. All right. So j must be k. J must be equal to k for this term to be non-zero. So I just put j equal to k. That gives me sum I less than or equal to j less than or equal to L. All right. What's that say? If I is less than j and j is less than L for all the things in the summation, that means that I is less than L. But hey, I less than L means that EIL is in particular one of those matrix units which is upper triangular. And so there you have it. Sum of upper triangular things is of course upper triangular, and that proves that AB is upper triangular. Similar calculation will show you that a lower triangular matrix multiplies by a lower triangular matrix to give you a lower triangular matrix. Next up, a nilpotent matrix. What's a nilpotent matrix? Well, a nilpotent matrix is one, if it has degree k, that means that it's a non-zero matrix, and like the first power, the second power, the k minus 1th power, all non-zero, and yet somehow the kth power of the matrix is 0. It's easy enough to give examples, like this n is 3 by 3, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 0. Obviously non-zero. You square it. Obviously non-zero, right? But when you cube it, that 1 kind of goes off the edge, and you get n cubed is 0. So this is a matrix which is nilpotent, degree 3. All right. So nilpotent matrices are kind of neat. It turns out that if you take an identity matrix plus a nilpotent matrix, it's going to be invertible. Here's the proof for n equals to 2. Suppose you got nilpotent degree 2. Then I claim that I plus n has inverse I minus n. You can see by multiplying. So I get like I squared, which is I, plus n minus n, so they cancel, minus n squared, so that's by assumption 0. And so what do you got? You got I. And vice versa. I minus n times I plus n is I. So it goes to show you that I plus n inverse is I minus n. All right. So that's kind of neat. Finally, that brings us to block matrices. All right. So I'm going to stop and start again. Just going to go get a glass of water right quick.